Welcome back to Python for Data-Driven Engineering. In this exercise, we're going to be covering number 6, NumPy, and this module has these separate activities right here. To install and import NumPy 1D, 2D, and higher dimensional arrays, we're going to export and import data. We'll talk about unary operations, meaning that you operate just on a NumPy object with one object, and then binary operations is where you have two objects and you operate, maybe you add or subtract those. Okay, so we have all of these. Let's go ahead and get started on this. Let me give an overview first of where we are and just how to access this information. Just come to APMonitor.com/DDE. And that web page is the Data-Driven Engineering course. Come here to the Python overview, and it gives an overview of the different modules that we're working on. We've already done 1 through 5, and so we're going to do number 6 now, NumPy. All right, now NumPy, the very first thing that we'll see here is we have these different 5 sections, and then at the very end, you're going to have some knowledge checks. So if you think you know NumPy already, go ahead and skip down to these knowledge checks and just challenge yourself to see if you can answer all of these. All right, so let's go ahead and get started. You can either access the notebook either here through the GitHub link, and this one you just need to save link as, and then save it somewhere where you can open it with Jupyter Notebook. Or you can come back here and just run it through Google Colab. Now, Google Colab, you don't need to install Python. Everything runs through your web browser on a cloud-hosted platform. But I'm going to go ahead and just do this through Jupyter Notebook. All right, so when we come down here, we'll see NumPy install and import. Now, Anaconda and many other packages come with NumPy and SciPy and other foundational libraries, so you don't necessarily need to install it. But let's say you don't have it available. You would just come to your search here and search for Anaconda prompt. All right, and then pip install NumPy, or open up a terminal if you're on Linux or on a Mac OS. Okay, it says it's already satisfied. You can also upgrade it if you want to, the _ upgrade. And so I'm going to upgrade to NumPy 1.24.1. It uninstalled 1.23.5, so I have the latest one. If you have this error right here, the access is denied, then just add -- user. Okay, and that will install it locally if you have like an administrative account that doesn't allow you to upgrade it. Now this was looks like a problem with something else there. Okay, so it looks like it's installed correctly. I'm going to go ahead and just restart my kernel, okay, to be able to use this updated package. So let's go ahead and just import NumPy, and we typically shorten the name, so we do as NP. But there are different ways to import NumPy as shown here. You can import just a specific function that you need, for example, the array function, or you can import all of NumPy. Now, there are many different functions that we can use, and this is just a list of some of them here. Arrays, horizontal stacking, linearly spaced values, okay, max or min. You got the mean, you generate a matrix of ones, you reshape it, you sort, get the standard deviation, shape, transpose, vertical stack, and generate an array of zeros. So many different methods and also properties that are there in the NumPy package, many more than just are listed here. All right, so let's go ahead and create an array with NumPy. Okay, so we have, first of all, a scalar. All right, so we can say y equals an array just with a single value. And let's go ahead and just print this out and also print the type. Okay, so NP is not defined. I forgot to run this cell right here. There we go. I'll run that one first. And there I have it. A single value, a scalar that's stored as an array as a NumPy array. All right, here's a one-dimensional array as a row vector in NumPy. I'm going to create an array with 0, 1, 2, 3, and 4. All right, and then let's go ahead and just print y. All right, so there we see our array. All right, let's go ahead and print this length and the length as well. So there's our if I do print y, then I'll see those values. And also if I do the length of y, I see that it's length of 5. All right, so that's a one-dimensional array or scalars. Now let's go on to two-dimensional arrays. So now in terms of the topics here, we have covered 1D. Now we're going on to two-dimensional now. Okay, so Z, I'll just call that Z, and I have my first row, my second row, and third row. And let's go ahead and print Z and also print its type as well. All right, so there's my matrix or a two-dimensional array of values. And you can see it's a NumPy ND array. All right, let's get the length of this. This is going to return the number of rows. So I have 3 rows and 4 columns. I can use np.size to get the total number of array elements. So that's 3 times 4, and that's 12 elements total. If you use the np.shape, that will give you the rows and columns. Okay, so 3 by 4. So rows are always listed first and then columns. All right, let's go on to higher dimensional arrays now. So this is a 3D array. All right, this is especially used for things like images. All right, we're going to just import matplotlib as pyplot, or pyplot as plt. Okay, this is just to be able to show the image. I'm going to have a red pixel, a green pixel, and a blue pixel. All right, and let's also have a white and a black. All right, let's create an image, and I'm going to have an array of red, red, blue, blue, red, red, blue, blue, green, green, blue, blue, green, green, blue, blue, and then black, black, white, white. And then let's go ahead and just show this image. Okay, so I've created a 3-dimensional array now, and you can see it's plotted it here with each of these pixels, each of these individual points are plotted, and you can see the pixel count here. Okay, so there's the one on the bottom. So in each one of these, I could replace that R by the 255, 0, 0. So you can see the brackets here. Those define what level. Okay, so at the most inner one, those are the individual pixels. Each row is each row of this image, and then the column is the column index of the image. So it's a 5 by 4 by 3. All right, let's use our np.shape. We're going to get the height, width, and the color. Okay, and we'll do the shape of image, and then let's print out height, width, and color. So there you have a 5. Okay, that's going to be the 5 rows right here, the 4 columns, and then each individual pixel indicated by the crosshairs here. That one is 3. So there are 3 numbers that define the pixel in terms of RGB. All right, and let's go down now to exporting and importing data. So we're going to go down to this one now. Okay, how to import data, how to export it in different file formats. So if we had this binary image file, okay, it would look something like this if we wanted to try to save it. So we wanted to make it human readable when we need it human readable. Okay, so if I save this, you're going to see an image file that comes out right here. I'm just going to edit this with a notepad editor, and you can see it's not human readable. Okay, it's machine readable. It's a binary file versus an ASCII file. So binary files are not human readable, but they are more compressed. They're computer readable. The computer can read those in. There are parts of it that are human readable, but for the most part, most of the file is stored as zeros and ones that are not intelligible to us without some decoding. All right, let's go ahead and go down. Let's save multiple arrays. We're going to save Z. This is like saving it into a single data zip file. And I'll say that F1 equals my image, F2 is Z, and then F3 is Y. So here I've created DZ, added the extension .npz. If you don't see this extension, you can always come to your folders and then under folder options. Okay, so let me see, on this new Windows version, I need to find folder options. Okay, there's options, and then if you go to view and then you unselect this hide extension for known file types, then it will show you your file extensions there. Okay, so let's go to loading data now. Again, this is a zipped file. It won't necessarily show anything that is intelligible here for us in terms of human readable form. All right, go ahead and close that one. Let's go ahead and load data now. So we save those, and we're going to say data equals mp.load. We're going to load that back in, and then we want to access, just like we saved here, F3 was equal to Y. We can access that now as a dictionary element, okay, where we load in data. Data is going to be a dictionary of values, and F3 will be that value that we stored there. So there's our array 0, 1, 2, 3, and 4 that we had saved as Y earlier. Now let's make them human readable text files. They're going to take up a little bit more space, and they don't import. Sometimes there's some encoding that you have to do to tell it what type of delimiter that separates the numbers, or column headings and things like that. But let's go ahead and just save the text file, z.txt. There's Z, and here is a text file now, where now we can see that it saved it as something that is a little bit more human readable. Okay, but it's still separated by tabs here. If I view, let's see, show symbol, show all characters. Okay, I guess that's just a space there, and we have our carriage return and line feed. Okay, for Windows, Mac OS, or Linux, they might put a different end of line character there. All right, so let's go ahead and switch to comma separated values instead, and add a header and maybe change the formatting a little bit. Maybe we don't need this much precision right here, the 64-bit number. Maybe we're okay with it being a 32-bit number, for example, or fewer decimal places that are listed there. So let's go np save text. We got z.txt. I'll save Z, and then let's add a few more options. All right, I can add a header. Okay, column 0, 1, and 2. And I also put in comments, and I put just a blank here. All right, so let me go ahead and just run that one. And let's reload this. So here is my new file. All right, and then just as I run this, we'll reload this and just look at it again. Okay, let's also add delimiter as comma. So when I rerun it, okay, you can see now it's separating the values by with commas. All right, and then let's change the format, okay, to just 8 decimal places per number, and still stored in scientific notation. All right, so it shortened it down a little bit. Let's not view all of the characters. All right, so there we go. So I have this file right here that's a little bit more human readable. All right, so there's some other common format specifiers. In addition to this E value right here, you can use assigned to integer E or capital E, F or F. This is one that I like, the G, because it stores it as a floating point number if it has certain qualifications for the number. If it's really large or really small, then it's going to store it as a scientific notation, but otherwise it'll store it as a floating point number. So it makes it even more human readable. And then you can also do it as a string. Okay, so let's talk about unary operations now. So we're on to the next one. All right, so unary operations. These are operations where it's performed on a single array within NumPy. All right, so an example is to reverse a sign of all the numbers in an array. So if I just print this out, it doesn't change z, but it shows me the result of going from printing z to print negative z. All right, so there's my original matrix and then my modified one. All right, so we have mathematical operations, some other ones. Here I'm going to do 1 divided by z plus 1. Now it's going to operate on each of these elements individually. So I didn't need to specify, like I want to do this on element 0, 0, first of all, and so on. You can just put your matrix in here, and it figures out that you want to apply this transformation to all of those values individually. Let's go ahead and transpose the matrix. Okay, so z dot transpose, and it'll just flip the rows and columns of this matrix. Let's convert to another data type. Okay, we can go as type, and maybe we want to save it as a string. So this one, instead of as numbers, we're just going to save it as characters. So that'd be like an A, B, an ASCII characters instead of storing it as a number. All right, let's look at the array index. Now with if you have lists and nested lists in Python, you have to use instead of this, you have to say my first row, second column. You can use that as well, but when you're dealing with NumPy, you can just do 0, 1. Okay, which makes it a lot easier to read. So row and column index. So that's this value right here. All right, let's look at the last value. So that has -1. That's going to be the last value. And the second to last value is -2, and so on. Okay, so this one is z of 22. And if I go ahead and just print out z, I can see that I went to the last row because I had a -1 there. And then the second to last column, which was the equals the 22 right here. All right, I could have accessed that same thing with a 2, 2. Okay, so that would have been the same answer, but if you want to go all the way to the end and say I want the last row or the last column, you can put in the -1 there. Let's look at array slicing as well. So I have 0 to 2. And this is going to give me the first 2 rows. Now, it is not like this. It doesn't include that last number, so you always have to put one more than you want. So let's look at the last 2 columns of any matrix. Now, those are available if I put in leave out a number here. Okay, so I start at the beginning. It's implied. And then this, it says, go from 0 all the way to the end. So I just want the last 2 columns of this matrix. Okay, so let's go ahead and print z. Okay, so let's see. Oh, it started at 0 and then trimmed it to say go to the last 2. So it's just these 2 right here. All right. All right, so this is a range. It's implied 0 to the second to last. All right, the third index refers to a step size. Now this is very useful for reducing the data. So there's a row increment. If I leave these ranges blank, then this is going to take every other row. So let's just look at Z again. All right, and then every other row, I'm going to take this row, I'm going to skip this one, and then I'm going to take this row. Now we can also reverse the order with a -1 there. Okay, so I've flipped the row indices, so the last one is first and the first one is last. Now we can also do a matrix inverse. Now this is only applicable to square matrices, and you'll notice that Z is not square. Okay, so the shape of Z is a 3 by 4, and so we want to make it a 3 by 3 instead. So if I just say, let's say I want all the rows, and then I just want to go from 1 to the end. Okay, then I have a square matrix, and now I can do the inverse of that. Okay, and there's the inverse. Looks like it's almost singular, very high values here. All right, binary operations. So this is our next one. And this involves, this involves two arrays. Now operators are available for scalars, are also available for NumPy arrays. So we have things like the plus, minus, multiply, divide, the modulo, remainder after division, floor division, exponential, and the dot, matrix dot product. All right, so let's just go ahead and add two of these together. It's going to take each element and add them together. Okay, we can also divide. Okay, again, it just takes each element and does Z divided by Z plus 1 for each element. Let's do some array multiplication. All right, and so here is Z transpose times Z. The @ sign is our dot product. So we can either do this or we can do np dot dot of these two. It gives us the same result. But I really like the, this @ sign. Makes it a lot easier to read, and it's more compact, more Pythonic. All right, let's look at comparison operators as well. And this will return a true or false for each element as a new array. And this is really valuable for data filtering. All right, so B equals Z minus 5 greater than Z divided by 2. So if Z minus 5 is greater than Z divided by 2, then it's going to be true. So let's just look at all the values that are true here. So it looks like beyond, let's just print Z as well. Oops, print. Okay, so beyond 11, so we have 6 here is greater than 11 divided by 2. This should be 5.5. So that's where the cutoff is, and then it becomes true after that point. So we can use the np.where command to select only the subset that are true. And then we can reshape to get a flattened array into the desirable form. All right, so where it's not B, okay, so here I have 1, 3, and 10, or if I said B, then I would just get the ones that are true there. Okay, so the not operator, this is where it switches all the falses to trues and all the trues to falses. All right, let's add to an array. Okay, so we got append. And let's add another row. All right, and there you can see I'm going to append to the end of this. All right, and let's go ahead and print Z. All right, so this flattened it and just added those 4 values at the very end. All right, but if we want to preserve the dimensions, we'll have to use the VStack instead. All right, so we'd use Z and then these additional row. And there you can see it's vertically stacked them. So it took Z, which is right here, and then vertically stacked on top of that this new row. Okay, so here is the horizontal stack as well. So what I'm going to do is say A equals np.reshape, and I'm going to reshape this into a column vector, okay, like is shown right here. So before it's a row vector, I'm going to reshape it into a column vector, and then I'm going to horizontally stack Z and A. All right, and let's go ahead and print this out. So I've added these -1s over here to the right. Okay, so horizontal stacking, vertical stacking, it's ways to augment an existing matrix with additional row or additional column. All right, let's go on to our exercises now. So now we're going to test your knowledge. I have some on this course website. If you need the answer, if you're stuck on it, then just come down here to show solution, and you can see the solution when it expands. Okay, I show some different ways of doing it. But let's create a 5 by 5. And so I'll do that with 1s. And I'll create that as a 5 by 5. All right, but I need to modify the array to place 0s along the diagonal. So I can do that in a couple different ways. For I in range 5, then we can say that y I comma I equals 0. All right, that's maybe the most intuitive way to do it with a loop. But we can also just use some of the built-in functions. So if I do np diagonal, and then I have 1s, and I make 5 1s there, then I get the same result if I do this. If I just take my 1s matrix of 5 by 5, I create a diagonal matrix with just 1s along the diagonal and subtract that from this original matrix. And that also gives me this. Okay, so let's go on to exercise 6b. Let's go ahead and first of all just create 20 random numbers. All right, we're going to just look at the index of where the largest one is. All right, so let's just look at I. So our largest one is at 18. Every time you run this, it regenerates those 20 random numbers. But let's, using the index I, let's print the highest number. So to do that, that's going to be Z bracket I. There's our highest number. And if I rerun this again, I'll get a different highest number. Let's go ahead and just print out I and Z. And then just to also verify, let's just print Z as well. All right, I'm going to do one until it gets a little bit lower number. Okay, there it is. 0 is my first one right there. And you can see that's going to be higher than any of the other values in that array of 20. All right, let's go on to 6c now. We want to create 20 uniformly distributed random numbers between 0 and 1. Okay, so here are 20 numbers. Use the np.where function to create a new array with values from z that are greater than 0.7. So let's go ahead and just print out z first of all. We just want to keep the values that are more than 0.7. Okay, so just those values right there. So let's go ahead and just take, I'll say y equals, and then I'll use the np where z is greater than 0.7. All right, and then let's print y as well. Okay, so, oh, and then I need to say that those are the indices of where Okay, so then we're just going to take z and say that I just want those values. Okay, so it took all of them. All right, here's the first one right here. Okay, 0.79. There's a second one. Here's another one. Another one. 0.85. There's another one. And then 0.76. Okay, and the rest of them are below 0.7, so they were not included in this new array where z is greater than 0.7. Okay, so a good way to do some filtering with the np.where function, and you can add some logical conditions here of what you're looking for in terms of the values. All right, let's go ahead and save the array, okay, as a text file. All right, so I'm going to take this one, and then I'll do np.save.txt, and I'll save z, but I need to give it a name. So I'll give it z1.txt, and I'll save it here. Here you can see the values of z1. All right, let's go on to the final one now. Calculate the dot product of matrices A and B. So let's go ahead and just, first of all, put in our A and B matrices. There's 1, -1. I'm going to create a new row, and then 5, -7. All right, I'll copy this syntax, and then just add the new values. All right, and there's two different ways of doing this. You can either do np, I'll just do this, c equals np dot a comma b, or you can do d equals a and then the @ b. And if I print c and also print d, I'll see that I got the same answer for those. All right, so there are many things you can do with NumPy. It's a foundational package for many other Python packages, especially in scientific computing, including a package called Pandas that we're going to be reviewing next. Now, NumPy, a lot of the functions you can use directly, and they're very efficient. They'll be able to, they're designed, some of them call Fortran functions or C functions that are compiled to be able to process very fast. So even though Python is not the fastest language, a lot of times the processing that occurs with NumPy occurs with Fortran or C functions that are very fast. So it's a very nice package. Probably should have been included as a base package within Python. But Travis Oliphant, he has some, one of the creators of NumPy, he tried to convince the developers of Python to allow that, but it's not one of the core packages. But I think as we go on, maybe some of those functions will be included into the core packages of Python, but if not, you can import NumPy and use all of them. All right, so up next is going to be Pandas, and we're going to cover a tutorial, again, fairly in depth on Pandas, just like we did on NumPy.